Yeah, there's been a lot of technical today. Yeah, this is going to be like totally zero math. It's going to be a break from the extremely technical. But I hope it'll be interesting.
And math. Oh, math.
Yeah. Okay. What kind of math?
Symplectic geometry.
Okay. Oh. Okay. 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 Yeah. What drew you here?
Oh, I like the thing you linked on, like an evolutionary perspective of cosmology.
Ah, good.
Let's see what this is about.
Great. Okay. I guess I should start, and if more people come in, they come in. Yeah. So I'm going to talk. Let me see. First, I'm going to get my bottle of water. Okay. Well, that's not my bottle of water. That's someone's bottle of tea. This is my bottle of water. Okay. So I'm basically going to talk you through three-stage cosmological natural selection, which is it's a version of Lee Smollen's old theory, cosmological natural selection, which is about 30 years old. It's been developed over the years by people like John Smart there, actually, and Clément Vidal and others. And recently it's moved to a kind of a three-stage model where there's three different forms of black hole production. And now it actually makes predictions about the early universe, which the James Webb Space Telescope seems to be validating. So it's become quite an exciting time to explore this very underexplored theory. And I think it has implications for AI alignment, which is surprising for a cosmology, but we can get to that at the end. We'll just go through the whole thing. I was doing some slides. I didn't really finish them because I got into these really interesting conversations. So the slides will be they will peter out, okay? Also, I'm not used to doing talks with slides, so they may not work too good. A starting point is, what is the problem that this cosmology is trying to solve that others don't? And it really comes down to Gauss's law, that a complex system that works is invariably found to have evolved from a simple system that worked. And this just seems to be true everywhere we look. You start with the telegraph, which is a one-bit, one-wire communication device, and you iterate generation after generation with human beings as the replicators, and you evolve iPhones. Societies evolve. You start with hunter-gatherers, and you iterate with, again, humans as the replicators. It's not quite as directional as technology, where we know what we're trying to evolve towards, but you do end up going through step-by-step. Societies get more complex until you end up with the kind of societies that produce, Singapore. Biology is the best known and best studied example of Gauss's law. You can't start off with sophisticated, intelligent human beings. You do have to start off with, prokaryotic bacteria, or my biologist friends always argue that prokaryotic bacteria are not in fact simple, and you have to start with, autocatalytic sets of, chemical processes that manage to replicate. So it's universally true that any complex working system that we've ever observed iterated into existence through an evolutionary process from a much, much simpler working system. Universes are the meta-container for all of these things that we've observed this to be true for. It seems to me and to some others that it would be unlikely that evolution would stop being the explanation at the membrane of space-time around our universe. That evolution might be evolution is the only mechanism we know that can generate these self-complexifying, self-ordering systems, and we seem to live inside one. So maybe evolution is the explanation. Now, yeah. Our universe is membrane-bound, it's self-complexifying, it's self-organizing. The energy that flows through it organizes it, which is a characteristic of biological systems, but we're increasingly finding that our universe self-structures by controlling its energy flows. We're seeing that the jets from supermassive black holes seem to have, which are unbelievably directional energetic processes, are helping structure the early universe. There's just seems to be something analogous to metabolic pathways. You're not just seeing random gas radiating randomly, bumping into itself randomly. You're seeing at every level of our universe something analogous to metabolic flows. You're seeing the energy that flows through the system, organizing the system. And a very obvious example is sunlight on Earth, helping organize the biosphere, but there's many, many examples. And it just seems extremely fine-tuned. The original version of this theory came from Lee Smolin, the theoretical physicist, partly to explain fine-tuning. If you adjust the basic parameters of matter in our universe by very much, you don't just stop something like intelligent life happening, you stop elements from happening, you stop atoms from happening. If you change the strong nuclear force by very much, or the mass of the electron by very much, you don't even get recognizable complex matter of any kind. So why is it so fine-tuned? There's a stance from which that isn't even a real question, it just is the way it is and whatever. But there's a stance from which you can say, that's a valid question. It's unbelievably unlikely the parameters would be balanced in such a way as to generate self-complexifying, self-ordering matter that goes from a hot gluon gas, incredibly smooth hot gluon soup, to us talking to each other through technology inside a biosphere that is self-sustaining over billions of years. Okay. So Lee Smolin was a theoretical physicist. He came up with cosmological natural selection, which was a possible mechanism of evolution for universes in 1992 in a paper called Did the Universe Evolve? And it was left on a hillside to die. It was an incredibly powerful and interesting theory, but it essentially didn't get developed for what I think are essentially sociological reasons rather than scientific reasons. I think there's been kind of a catastrophe in that one of the most interesting ideas that have come out of any field of science, I think, in the last 30 or 40 years, was born in a place where nobody took responsibility for it or developed it. So actually, I'll just sit on that for a second, and I'll expand on that for a second. It was thought up by a theoretical physicist. He published it as a side project. He published it in the Journal of Classical and Quantum Gravity, which is read by maybe 100 classical and quantum gravity guys who had no understanding, no evolutionary background, didn't know what to do with it. Cosmologists said, well, this is an evolutionary theory. We have no evolutionary background. It's speculative. They didn't really do much with it. The evolutionary biologists who would have had the background to play with this theory and do something never knew it existed. I had lunch last month with Dennis Noble, who's one of the great evolutionary biologists of the last century, and he had never heard of the theory. He was fascinated by it. He dragged out the lunch and kept talking to us afterwards and brought us back to this senior common room in the Balliol to keep talking about it. He loved it. But he'd never heard about it. 30 years that theory's been sitting around. Minds like Dennis Noble's should have been playing with this for the last 30 years. So I think there's a kind of a sociological catastrophe here that's also part of the story, so that's why I'm mentioning it. The original version of cosmological natural selection argued that it argued that universes reproduce through black holes and big bangs. That's an extension of John Wheeler's idea. John Wheeler, the great American physicist, who said we have two problems in our universe we don't know how to solve. One is, and that both involve singularities. One is black holes, where mass energy collapses to a point and basically disappears from our universe. We don't know what happens. And the other is the Big Bang, where mass energy appears from a singularity and expands out to form a universe, and we don't know where it comes from. And John Wheeler's solution was, what if they're opposite sides of the same thing? What if a black hole collapsing to a point in a parent universe bounces to expand out to form a child universe, a new bubble of space-time outside of the original parent universe? He also said, well, what if the basic parameters of matter in the child universe were randomly different? That was interesting. It was, but it didn't you were just throwing an infinite number of random universes at the problem, and maybe you get a complicated, self-complexifying one as a result. It's not satisfactory, but it was interesting. The really good bit was attaching the black holes to the Big Bangs. One of his students, or someone he mentored a little bit anyway, Lee Smolin, was reading a lot of evolutionary biology on the side, and he realized from his reading in evolutionary biology that if the child universe, instead of being randomly different in its parameters, just had a slight variation in parameters, you would automatically get Darwinian evolution of universes. Because the variation in the child universe would make it either more likely or less likely to produce black holes and therefore be more or less reproductively successful. So the ones that are more reproductively successful produce more offspring, bring that variation with them. You then get variations, slight variations on that variation, some of which will be more likely to produce black holes, some less. And so you can see over time, you will get runaway reproductive success. You should get universes that produce huge numbers of black holes, of offspring. Even if your starting point is the earliest, most primitive universes only produced 2 offspring, 3. It's going to go up and up and up over time. They're not in competition for resources. There's nothing to constrain them. They can have extreme reproductive success. Now, our universe has, so far, according to the most recent survey where they worked this out, has already produced 40 quintillion black holes, it's a lot of black holes. Now, there are bigger numbers, yes, but compared to, if you imagine a starting position of a handful of black holes, 40 quintillion is a hell of a lot. Now, this is a timeline for the development of the theory. That was the original version of the theory. To understand what happened, you have to know that in Smolin's time, they only knew about stellar collapse black holes, where a star reaches the end of its life, runs out of fuel, the radiation stops pushing the matter out against the gravity pulling it in. It collapses under its own gravity and forms a star-sized black hole. So he had a limited single-stage model which just assumed stellar mass black holes. It wasn't able to make many predictions, made 1 or 2 predictions that are still holding up on neutron star mass and that, but not much. In the 2000s, Clement Vidal, John Smart's there actually, Price, Louis Kane, they expanded this to a 2-stage model, adding technologically produced small black holes, because they were wrestling with the problem, why would a universe produce intelligent life? What's in it for the universe? How does the universe as unit of selection get a reproductive benefit from putting all the energy required into producing intelligent life? And there's an interesting solution to that. Life forms optimize for energy efficiency. All life forms try to use energy as efficiently as possible. This is just an unavoidable universal truth, because if you don't use your energy as efficiently as possible, something will outcompete you by using it more efficiently than you do. So anything that survives uses energy really efficiently. The most efficient so there's a logic of increasing energy efficiency. We used human muscles, then we used animal muscles, then we burned things in wood, oil, gas. Then you use solar and wind turbines. Then you use nuclear fission, which can turn up to 0.1% of mass into energy. Then you use fusion, which can turn up to 0.7% of mass into energy. But small technologically produced black holes can turn up to 42% of mass into energy. So they're 60 times more efficient than fusion. So any intelligent life form that wants to optimize energy production is going to converge on the technological production of small black holes for energy production. So if life ever developed inside an evolving strain of universes and did that, it would be producing so many more black holes per unit mass than a stars or direct collapse only model, that it would just have runaway reproductive success, huge number of offspring. So the 3-stage model that I'm exploring says that first you get supermassive black holes in the evolutionary history of universes. Then later there was a breakthrough to produce ordinary medium-sized black holes from stars collapsing, and later again life produce small technologically produced black holes. These happen at 3 different evolutionary eras, but they're all conserved inside our universe because each builds on the one before. You can't just throw it away. You can't throw away your primal means of reproduction just because you found 2 better ones that build on top of it. For example, like human beings still reproduce through fertilizing an egg in salty water because our jawless fish ancestors first reproduced that way. You can't jump to a completely new method. So we're arguing that supermassive black holes that we find in our universe, because we see a supermassive black hole at the center of every galaxy in our universe. We know that there's a supermassive black hole with a mass of millions or even billions of solar masses. So like the biggest ones are like something like 42 billion solar masses, the largest ones. The argument is that evolution is going to conserve that method of reproduction. They will form by direct collapse, just big sheets of smooth matter collapsing to form them directly without forming stars on the way down, anything like that. Then ordinary medium-sized black holes come from stars. There's 1 trillion supermassive black holes in our universe because there's roughly 1 trillion galaxies. That's order of magnitude correct, but it might be twice that, it might be half that, but there's basically about 1 trillion supermassive black holes because there's about 1 trillion galaxies with them. Ordinary medium-sized black holes, star collapse black holes, there's 40 quintillion so far. And small technologically produced ones, the numbers could be crazy because an optimum size for that would be around the mass of Mount Everest or something. If you don't want it to evaporate and you want it to last as long as possible, and you want to be able to actually maybe move it in space or whatever. So they would be crazy numbers. So the interesting thing here is that we potentially have all 3 of those in our universe. They all build on top of each other. I just drew with a pen like what this might look like so you can just see it. This is a very crude drawing. But basically at the Big Bang, all the supermassive black holes we see today at the center of all the galaxies have to form very closely after the Big Bang. Why? Because that's the only time where the conditions in our universe are optimized for direct collapse supermassive black hole formation. It's very, very smooth gas. We know from the cosmic microwave background radiation that the gas is really, really smooth. There are tiny density fluctuations of roughly 1 in 10,000, and those density fluctuations obey a power law distribution where there's a very small number of big fluctuations and a very large number of small ones. That power law distribution looks extremely like, in number and in proportion, the power law distribution of the sizes of supermassive black holes in our universe. That's not conclusive evidence, but it's very suggestive. So all the supermassive black holes form there, about 1 trillion of them. After the supermassive black holes have formed, they optimize the conditions for star formation. It's actually hard to get stars from gas as smooth as we see in the cosmic microwave background. I think it's optimized for direct collapse black holes, where you have huge territories of gas collapsing. If there were density fluctuations, they would nucleate out into stars. You couldn't do it. So the stars then come afterwards because the supermassive black holes optimize for star formation. They form. Plasma falls in, it forms blazing hot donut of accretion disk of gas of plasma around the supermassive black hole. This generates a colossal electric field, electromagnetic field, blasts jets north and south from the north and south magnetic poles, shocks the surrounding plasma, nucleates out star formation. So you should get rapid early galaxy formation around supermassive black holes. So the reason I'm probably here today, and the reason people actually pay me to research this, is because I predicted that before the James Webb Space Telescope gave us any data on the first billion years of the universe. The logic of the evolutionary model says direct supermassive black holes must form by the original mechanism, direct collapse. They have to do it inside the first couple of 100 million years, because that's the only time that the gas is smooth enough to do it. After they do that, they themselves fuck up the gas so much by shocking it with jets that it's not possible to form supermassive black holes later on. There's no smooth gas left. But they optimize for star formation, so what you should see, and this was predicted by me before the James Webb gave data, is supermassive black holes generating rapidly and efficiently galaxies around themselves in the extremely early universe. When the James Webb finally came back with the data in 2022, that's what it's seeing. It's seeing rapid, efficient early galaxy formation around supermassive black holes that are dominant in those galaxies. Many of the galaxies we're seeing, they seem to have a supermassive black hole that's at least 10% the mass of the galaxy. We've seen one, UHZ1, a galaxy where the supermassive black hole is 50% of the mass of the entire galaxy. It weighs as much as all the stars in the galaxy put together. The existing models of structure formation are completely different and can't get you that. The standard model of structure formation for galaxies, spiral galaxies say, is that you get bottom-up, slow, hierarchical structure formation with small little areas falling, collapsing to form some stars. These little clusters of stars merge. You get up to 20 mergers before you get something that looks like a galaxy and before it starts to structure itself. And the supermassive black holes under the mainstream model usually arrive much later through mergers of stellar collapsed black holes and so forth. And that's not what we're seeing. We're seeing what I predicted back in 2022. Did you have a question?
Yeah. So the prediction was on the timeline, or like the numbers, or like total numbers of
the prediction. The prediction was that supermassive black holes would form first. This wasn't in the mainstream model. They would form first, they would form by direct collapse. Now, it was predicted that it was possible to have direct collapse supermassive black holes. Priya Natarajan, Avi Loeb, Volker Braun, several other people had written papers about 20 years ago saying it was technically possible, they thought, to have a small number of direct collapse supermassive black holes, but they positioned those after the first stars, and they thought it was very, very rare and unlikely. My prediction was it's not rare, it's not unlikely, and it's not after the stars. It's before the stars, it's ubiquitous. So that was the big gap between my prediction and the mainstream prediction. Basically, under this model, it's all one thing. You've had three kind of evolutionary breakthroughs. One is direct collapse supermassive black holes. At some point, some exploring the possibility space for matter. You had some matter left over that managed to form stars that made stellar collapse black holes. That's a lot more black holes per unit mass, so it's a conserved evolutionary breakthrough. At some point, there's some mass left over. The possibility space for matter gets explored more. You get planets with biological life possible, and they make small technological black holes. That's a huge breakthrough that gets conserved. So you've got the whole evolutionary history with the multiple breakthroughs in it, but it makes it all one thing. So basically, biology is this is the t-shirt version of what we're arguing here. Biology is the first half of the periodic table coming to life. Technology is the second half of the periodic table coming to life. It's a developmental step in an evolved universe. So matter has been fine-tuned by this process over many, many generations. The earliest breakthrough into life was probably very difficult, very late, very partial. Matter wasn't optimized to do it. It's something that you stumble into. But once you've stumbled into it, the offspring universes are very, very numerous. They explore the possibility space for that matter, and they fine-tune it. So, phosphorus is fine-tuned. Carbon is fine-tuned. A very seductive and interesting point here that is not proof of anything, but is suggestive, is that carbon, nitrogen, and oxygen are part of the CNO cycle in fusion in stars. There are two fusion mechanisms in stars. One is the proton-proton reaction, proton chain reaction. That, under evolutionary logic, that has to have been the original reproductive fusion mechanism for stars, because it's proton-proton, you can do that just with hydrogen. So you can do that in a universe that hasn't developed other elements yet. Once you're doing that, though, you can start fusing, you start to develop elements, you start to explore that possibility space over multiple generations of universe. You can get to carbon and nitrogen and oxygen, and carbon, nitrogen, and oxygen do this beautiful catalytic fusion reaction that generates more elements and is highly efficient and makes stars better at fusion. So you can see that being conserved as a fusion mechanism for stars. But what is biological life based on? What elements does biological life base itself on? Carbon, nitrogen, and oxygen. So what that looks like from an evolutionary point of view is a classic example of exaptation. Exaptation is in biological evolution where a complex, something relatively complicated has developed for a specific purpose, and then it gets adapted by evolution for a completely different purpose that is reproductively beneficial. And the classic example is the swim bladders in fish. A swim bladder is a big air bladder inside a fish so it can control its buoyancy. When fish moved up onto land, the swim bladders were exapted to form lungs. So lungs didn't have to be invented from scratch. They were adapted from something that had already developed for a different purpose. And often big breakthroughs happen in that way. They don't come from scratch. They build on something that had already developed for a different purpose. And the CNO cycle looks like a really interesting and provocative example of that. It's developed for fusion in stars during the two-stage era where they're just producing direct collapse black holes and stellar collapse stars, black holes. But once you've got carbon, nitrogen, and oxygen, you've got a basis for a more complex life form on. And so the periodic table itself would have developed over time, would have evolved over many generations. And if you look at the periodic table, it has it looks like the kind of result you get from an evolutionary process. It's very ragged towards the end. It's very precise at the start. It falls apart towards the end in the way you would kind of expect an evolutionary the result of an evolutionary process to be, because you can't really stabilize the ones at the end maybe without destabilizing the ones at the beginning, but it's getting there over time, it's exploring the possibility space. Okay. There's two objections that I almost always get when I'm doing this, so I thought I'd just throw in both objections now and get them out of the way. One is, wouldn't universes get smaller in each generation? Wouldn't there be kind of conservation of energy, of mass? And then, no. Luckily, our universe is essentially flat. The positive mass energy and the negative gravitational energy in our universe net out to zero. Again, provocative and interesting that it happens to be that way, right? That makes a lot of sense if evolution fine-tuned universes so that you can make big ones for free. So you can basically make a full-size universe for free. In the same way that you can produce a matter-antimatter particle pair for free, as long as they're netting out to zero, you're clear. And that's the case with our universe. Does our universe really produce a lot of black holes? I can imagine a universe that produces infinitely more. Because I get this a lot from mathematicians, because they're mathematically, you can almost certainly come up with something that will produce an infinite number of black holes. But how do you get there? Our starting point on the evolutionary line we seem to be on is a very small number of very large direct collapse supermassive black holes. And you can get from there to here through the steps I've outlined. It's harder to see how you get to trillions and per cubic centimeter of black holes. The biological analogy is I can imagine a giraffe that produces an infinite number of offspring, but there's no plausible evolutionary route that can get me there. Material reality constrains the possibility space that you can realistically explore. That argument can get very complicated, and I'm happy to have it at some point, but that's my crude answer to the crude version of the question. This theory has other interesting consequences. The structure of our universe is peculiar. When we found out what that structure was in the 1970s, we were somewhat startled. 80% of our universe comprises voids. There's very, very, very little matter there, hardly any galaxies there. Largely empty. 20% comprises filaments. They're 10 times denser. They're basically rivers of plasma and galaxies. They tend to flow into nodes. Nodes are about 1% of our universe, and they're where all the galaxies cluster. There's really dense clusters of galaxies, clusters of galaxies at those nodes. And they're where the filaments join. The classic explanation for that structure is gravitational. To do it, you need an enormous amount of dark matter. And you, with enough dark matter in the right places, you can kind of collapse everything to sort of give you that structure. But it wasn't predicted in advance, and there's a possible alternative that comes out of cosmological natural selection, three-stage cosmological natural selection. So blowtorch theory is a structure formation model that comes out of three-stage cosmological natural selection. Blowtorch theory says that if 1 trillion supermassive black holes formed by direct collapse that early, when the universe is that compact and that dense, the jets they're going to produce, because they're going to automatically suck in plasma, spin it up, and shoot out jets. The jets they're going to produce are not just going to produce galaxies, shock out galaxies around them. There's actually a complex mechanism for that I'm not going to go into because it will just take us sideways. But they produce galaxies in a slightly more complex way with jets deadheading into really dense plasma, spilling out helical magnetic fields, getting in this overdense cocoon that then cools, collapses, and brings the helical magnetic fields from the jets down into a spiral into the protoplasmic disk, and which locks it into solid body rotation. There's a lot of details, but you can end up with a spiral magnetic field and a flat rotation curve through a purely baryonic model under this approach. But that's too detailed for this. Basically, the interesting thing is 1 trillion jets that early, when it's that dense, can carve out the voids and lay down the filaments that we see in the contemporary universe. The maths for this does actually add up. The energy budget is good for this. You're getting enough ergs per second out of those jets to push enough plasma out of the way to give you the contemporary voids, because at redshift 30, when the universe is 30 times smaller than it is today, which is 200 or 300 years, 200 or 300 million years after the Big Bang, the density is like 30,000 times higher than it is today of the plasma, because you're compressing all three axes, so it's by the cube of that. So you basically got 30,000 times the density, and in a much smaller space. So the cavities that are driven by the jets will be, as the universe expands and expands those cavities, and those cavities merge and expand, will give you the voids we see today. And the plasma that's pushed out away from those voids gets pushed into these filaments. They're the places where the plasma gets pushed to. And that's an alternative model for structure formation at the mega scale that doesn't require dark matter. I'm not saying there's no dark matter, because I don't want to get into any arguments with people who, because it does explain a lot of other things very well. But this model is agnostic as to dark matter. It doesn't need it. You can still have dark matter if you want it, it's fine, but you don't need it. This blowtorch model that comes out of cosmological natural selection, it explains, for example, the weak magnetic fields that we see in the contemporary voids. The mainstream model has a great deal of difficulty explaining why you would have magnetic fields in voids that don't have plasma in them. Where the fuck do they come from? Under this model, they're there because jets generated those voids and have left faint traces of the magnetic fields that come from those jets. Now, the jets from supermassive black holes are interesting because or from any black hole, because black holes tend to spin at close to the speed of light. The jet is coming out of that. The field lines are anchored around the black hole, which is spinning. So it spins the field lines as the jet goes up. So you get a helical, spiral staircase magnetic field around the jet. Now, one prediction made by this theory is that helical magnetic field will still be in the filaments that are the ghosts of the early primordial jets. And if that's the case, the flow of plasma along the filaments should be more laminar, should be less turbulent than it would be if just pure gravitational collapse randomly assembled these filaments, because the magnetic fields shouldn't be aligned in any particular way if it's just a pure random gravitational collapse model. So one of the things we're starting to look for, and there's already some suggestive evidence for, is surprisingly laminar flow of plasma in towards the nodes. And there is suggestive evidence that you do get surprisingly smooth flow, which you would get if there's a helical magnetic field guiding the plasma, like a rifle barrel, you know. And that as they exit the filaments and enter the nodes, they become turbulent, which is what you would expect under this model. So again, there's no conclusive evidence yet, but there's a lot of suggestive evidence. It also predicts and explains sharper density gradients at the filament void boundary, because the voids are 10 times less dense than the filaments. And the boundaries seem to be pretty steep. It's hard for gravity to give you a steep boundary. Like, gravity just declines over distance. You shouldn't get a sharp boundary. If, however, there is an electromagnetic boundary around the filaments and around the voids, if there are basically big electromagnetic bubbles, that will constrain the plasma flow across the boundary, and you should get a much sharper boundary than a naive gravitational passive collapse model predicts. And we're starting to look for that, and we're very close to having enough resolution to be able to tell how steep that step change is. But the model is predicting quite a steep step change there. And I think that's about, I think I ran out of slides at that point. So how about we talk about it? Because one of the implications of this, I'm talking to like Adam Goldstein about this and various people, is that this makes the problem of when does agency begin totally different, because it's all agency all the way up and all the way down. It's baked into the basic parameters of matter that we should develop intelligent life that develops technology that optimizes its energy consumption, that lives for a very long time and is very successful. That's very, very interesting, you know? Life isn't this, under this model, life isn't this separate, weird accident that popped up like mold on a dead universe. The universe is collaborating at every stage, and if you look at it, it looks like a complex system of systems that is highly directional. You need the whole periodic table to get life and technology. You need the whole fucking thing. And how do we get the periodic table? We get it in this highly unlikely way that looks fine-tuned by evolution. You have the first round of stars produce the first elements that aren't just hydrogen and helium. But how do they distribute them? They have to explode in supernovae to distribute them. How do they do that? The strong nuclear force is fine-tuned so that it's incredibly attractive at all normal scales, but when you compress it enough during the gravitational collapse of a star, it reverses. It flips and becomes a massively repulsive force, which explodes all of those elements out from the bottom of an incredibly deep gravity well and distributes them into the interstellar medium to enrich the hydrogen gas that is flowing in from the filaments that were laid down by the supermassive black holes at the start, so that you then have a second round of star formation from this enriched hydrogen. They go through their life cycle, develop a ton of more elements, explode as supernovae because the strong nuclear force is designed to do that, and distribute right out the bottom of an incredible gravity well. And then you get a third round of star formation, and it takes at least 3 rounds of star formation to build out enough of the periodic table that you can get planets with life and technology. And we're on a 3rd generation star, so maybe 4th. So it's a complex system where the energy that moves through the system organizes the system at all scales. It looks like this universe has every sign of something that evolved over an extremely long period of time to produce direct collapse supermassive black holes, but they are a very small part of the game now because the game has got more sophisticated, but they're still there. Direct collapse supermassive black holes. Stellar collapse black holes, very important because they actually are the necessary engines for building out the next stage, but they're still there. Everything builds on the previous stage. And a complex, ragged at the edges, periodic table that builds out living systems, biospheres, and allows them to build out technologies. It's all one thing. And that's the model I'm exploring right now.
Could you tell more about the mechanisms that introduces variation at the that like changes the laws of physics a little bit at the regeneration?
That's what's happening, but we don't know what the mechanism is. This whole theory is basically at exactly the stage that Darwinism was when Darwin published The Origin of the Species. He didn't know anything about genes, he didn't know anything about mutation rates, but he knew that this theory explained a hell of a lot. So we know this theory explains a hell of a lot, but we don't know what the mechanisms are. I am desperate for people to join in this field, explore it, because there is so much territory to be explored. What are the mechanisms? We need experts in a whole bunch of domains to play with this and see what they can find out, because clearly there has to be a mechanism of inheritance. What is it? We don't know, and so on.
Can you tell him about the Smolens 2008 paper? He made one speculation with a matrix block model where the gauge fields randomly reorganized to create the fundamental parameters. There's only one paper on it, and nobody has tried to critique or extend it.
Yeah, so there is an interesting approach to this. Yeah, that matrix paper is a very interesting starting point for exploring this idea. Again, nobody's built on it. This is a completely orphaned theory, and it's purely sociological. It's not scientific. It's not like this theory has been explored and disproved. It just has been ignored. And it's now making predictions about the early universe that are much more effective than the mainstream predictions. And I think it's really time to spread the word. Find your friends that might be interested in this, tell them about it, get them to join in. I'm going to move to the Bay Area later this year, and I'm setting up an evolutionary cosmology working group. It's wide open for suggestions. I think I can get research funding for interesting research directions if anyone has them. This is we might channel some of this through the Evo Devo Institute. John's involved in that, who have done a lot of work on this over the years. This is I think this is a golden opportunity for young researchers to really have fun in a field that I think will turn out to be very important. I could be wrong. There is a long history of crackpots thinking they know the secrets of the universe, but there's also a more modest history of people from outside a field pointing out an error inside the field that was just very hard to see when you were stuck in an old paradigm. Yes.
Well, I'm burning to know the applications to AI alignment.
Sure. I think one of the implications is that AI alignment isn't just a one-shot weird thing that we have been landed on us. It's a developmental problem that is going to crop up in the development of universes and has played out over evolutionary history in some way, and maybe that knowledge can give us some new ways of looking at the problem. Maybe there are biological analogs, developmental step changes that are similar in the biological realm that we can maybe learn something from. I do think that what Adam and Emmett are working on with organic alignment, natural alignment, is actually one way of taking this kind of approach and saying, maybe we solve this biologically. Maybe if this is an evolutionary developmental stage breakthrough, maybe we can learn from similar developmental stage breakthroughs in biology. But I don't know. It feels like a cosmology that gives you this process that we're all stuck in, where we're transitioning from biological intelligence to biology plus technology intelligence, that there's gonna be something there for us that will be hopefully useful. What we might find might be very depressing, but there must be something there. That's why I'm talking to you.
As if the universe wouldn't care.
Yeah.
Because the AI could also create these black holes.
Exactly. This is a slight worry. Is the biological substrate needed? Are we just bootstrapping the technological? I don't know. I don't know the answer. The thing that makes me think that maybe biology has a role, and this starts to get into hyper-speculative territory, is consciousness. the hard problem of consciousness is like, why the fuck does it feel like anything to be us? And also the problem of when you take psychedelics, why does the universe look like that? And when you meditate for like a long time, why does yourself go away? And why does there appear to be this field of consciousness peering through the pinhole of me and peering through the pinhole of you? And if a universe is an evolved system of systems, is essentially an organism, then the consciousness in that organism may be of the entire organism. And it's possible, but this is highly speculative. You do not have to believe this to believe the evolutionary theory. I'm just going way beyond the data. But it's possible that the universe has a field of consciousness, and we're the equivalent of electrons in the quantum electron field. We're the consciousness nodes in the consciousness field. And all of us are, in fact, the taste buds of the universe. We're the retinal, cones and rods of the universe. We're the point where the universe gets to know itself, look around, and act. And if that's the case, maybe we're an important part of the developmental process. Maybe AI gets to augment us, not replace us. But I don't know. Yeah. 4 minutes left.
Tomorrow I'm going to take a stab at it's called autopoietic alignment. So after the SLT, at 1 o'clock, I'm going to try and generalize this idea to, if the universe is an autopoietic system, what are the autopoietic objective functions? And I can propose 3 tomorrow that you could critique.
Yeah. And I'm also going to have a little meeting tomorrow where anyone who wants to help formalize this or work on it or develop simulations or whatever can come and talk to me. I'll take names, we'll get in contact. I can see if we can find you some funding to work on it. I just want to get more minds on it. I do have some sort of philanthropic guys who like this theory and are interested, and so that might be, come and talk to me if you think this is interesting to you and you're intrigued and you want to play with it. There isn't any money really much at the moment, but there will maybe be down the line. But don't do it for the money. This is just fascinating stuff. And if anyone wants to, I have a meeting tomorrow, and send your friends to it. If there isn't someone here but you think they'd find this interesting, send them to it, and we'll just take some names, work out a way to stay in touch. Yeah.
I'm curious, like the difference between thinking about this as like evolution over time versus like some like all worlds philosophy where like, everything exists and this is just, and is it just because like the data shows that it's like happening over time, or like why do you prefer this over that?
I prefer this for a bunch of reasons. Let's compare it to 2 other multiverse models, right? So the Everettian says every single possibility plays out over this one set of physical laws and parameters, right? So that's one set completely explored, and we happen to be in one of these because they're all there, and every possible thing happens. Okay, that's one. But that makes, we're quite unlikely. We're a tiny part of the full possibility space that gets explored. String theory would argue completely orthogonally to that. It would say there are an infinite number of sets of basic parameters of matter, and in one of those, this particular set comes up and happens to generate this kind of self-complexifying universe. Again, it's very, very unlikely and arbitrary that we happen to be in that one. This model says there's a tree of life. There's an evolutionary tree of universes, and we're along a particular branch that has had several breakthroughs in reproductive success, and along this branch, most universes are produced by intelligent life forms utilizing technology. This is a normal universe along this branch of the evolutionary tree. It's much less unlikely that we're here. It's actually likely we're here. It would be less likely if we were our universe was probably produced by a universe just like this that produces intelligent life. Mathematically, very likely that that's the case, rather than just a star, rather than just a direct collapse black hole. So this kind of universe is not a freakish outlier. It's kind of pretty normal along that branch. There will be other branches. There may well be more bacteria-like branches that just reproduce really, really, really fast and are very, very simple. That's fine. In this world, there's a lot of bacteria and a small number of human beings, but there's still human beings. And we're just in this that just seems much more satisfying to me. There's a likelihood to our existence here in that model that isn't there in the Everettian one, isn't there in string theory.
Can I follow up?
Sure.
Like the root of this tree, like how many laws of physics are assumed at like the root of the tree?
We're talking about 10 seconds left. There's 26, 27 parameters of matter. There's maybe 30 parameters of matter. There's a small number. It's just it's really masses and charges, and it's gravity, electromagnetic, the weak law, strong law. It's a small number, but they're so fine-tuned that they play out. And again, I think the search for mathematical beauty and symmetry that a lot of mathematicians do when they're looking for supersymmetries and that, they're going to fail because the beauty of the basic parameters of matter in our universe aren't in the parameters themselves. They're in the downstream consequences for the reproductive success of the universe. We are the beauty of that mathematics. So I'm out of time. Thanks. So I'm working on this in public on Substack on a thing called the Egg and the Rock. If you want to subscribe, you'll get the latest posts as I do them.